last lecture. Congratulations, you made it. You survived. So I want to, today's going to be a short lecture, but something which I ought to say a little bit about. I'm not going to say too much about because actually I don't know too much about it. I'm far from an expert on this. But the topic is internationalization and localization, which are almost always in software documents, abbreviated I-18N and I-10N. Count the letters. There are 18 letters in internationalization between I and N, so that's where that comes from. And it's much shorter to write. So, why do we need to internationalize our software, or localize our software? Well, the basic problem is that not everyone in the world is an English-speaking American. And while this is nice, while this is very interesting, while this is very interesting for travelers and makes, life more interesting, it's just a real nuisance for programmers. And once you think about that, you want your program to work and be useful anywhere in the world. You've got a number of things to worry about. Clearly, strings, all of your, anything that's in the UI that's a string, for example, your button labels, any error messages you print out, anything about that always has to be in the local language of whoever you are, whoever the user is. Let's see, formats. So in America, today's date would be like, I don't know, what's the date today? The 30th? It would be 1/30/01. In other places, it would be 30/1. Excuse me?
It's basically the rest of the world.
Well, right, you could, some places do the year first, and some places, of course, will not even use Roman fonts and will use kanji, exactly. So, let's see. Anyone know how that would go? Something like, I think that's right. Maybe there's another one of those. So you've got to have your program be able to put out all of these things, and it's got to do it the right one at the right place. Also, even numbers. In America, we would write something like that, and in other places, you would write it like that. Right. See, there's America, other places. So what else varies? Let's see. Currency, the currency symbols are going to vary all over the place. Each, if you are writing amounts, you need to swap in the right currency symbol. Even things like alphabetizing. European languages have different characters in the that they use in the languages, and they also are alphabetized, sometimes in different orders. So, for example, I think in Spanish, LL is alphabetized as a unit, is it not? And I forget where it comes in. But certainly an alphabetizing rule in English is not going to work for other languages. So you have to worry about these things. And internationalization is essentially the process of making your program so that it's big enough, and general enough to cover all of these languages. And localization is then having to somehow find out where the program is running and then select whatever subset of all of the stuff you've built in. When you internationalize, you basically make it work for everybody, and then you have to localize by selecting the particular subset of things that you need to run. What else do we need to talk about? Let's see. So there's the notion of locale in internationalization, and this is kind of a combination of a language and the country where it's spoken. So it's generally not enough to know just the country or just the language, since the languages vary in usage and accent between countries, and countries often have multiple languages. And as always, there's standards for representing these things. The languages are represented by a set of two-level codes, I think usually small letters. So English is EN, and I think Danish is DA. And some of these are what you might think. Some of them are different because they're the transliterated two-letter codes from the native pronunciation of the language. So Chinese is like ZH, and German, I think, is DE. And then, of course, countries, you have capital letters, and I forget whether this is CH or CN. Does anyone know what China is? CN? I think these are the same ones that you see on stickers on the back of cars. But so this mapping is some ISO standard, which I wrote the name of in the notes. And these are ISO standards, and then you often combine them separated by a dot to talk about a particular locale. And there's another syntax for adding on variants to these. But once you know this combination, you know how you want to localize. You know the target for which you want to localize your program. So you basically have the task of putting all of your strings and formats and collators and all these things into various packages and bundles associated with each locale. And then when you know your locale, you basically instantiate the right version of those and then write the rest of your program that always goes through this mechanism. So you don't sprinkle strings throughout your program. Let's see. One other interesting cultural issue to talk about that becomes a pain is character sets and encodings. In the beginning, when computer work started, it basically really the first couple decades were mostly UK and US work and was done in English. And the character encodings that were used were basically, the character set that was used was basically what you see on a normal typewriter. And as a matter of fact, the first UI terminals were essentially typewriters connected up to computers, and so there grew up out of that a character encoding called ASCII, which is still the most common, I guess. And this is a 7-bit encoding which has numbers 0 through 128, and they map to the normal typewriter keys: small letters A to Z, capitals A to Z, English punctuation marks, and the numbers. And that's about it.
Is that 127?
Yes, you're right. Right. The reason it's 7-bit instead of 8-bit is, although we want to send bytes back and forth, when this was being used, you were talking to your terminal, was talking to your computer through a serial line, which was sending 8-bit characters back and forth. And these things were very noisy, especially when you had teletypes, when every time you hit a key, this big honker relay would close shut and make quite a bit of electrical noise. So you would often get bit errors in here. And so the high order bit of this of this scheme was always set to 1 or 0 as a parity check. So if you have an arbitrary 7-bit number, you can set the 8th bit so that the number of ones in the whole byte is either always even or always odd. And then as long as you decide on a convention, the receiving side can do that parity check, and if it comes out with the wrong number of ones, then it knows that there was at least a transmission error. It doesn't know what it was, where the error was, but it's error detectable, so you can say retransmit this character. All right, so that's why ASCII is 7-bit, and but ASCII lives on. As computers got better, you got to use that 8th bit for something. Nowadays, we're no longer shipping bytes around that way, and we can really rely on pretty reliable transmission. So a number of 8-bit character codes arose, and people variously threw in, filled up the upper 128 characters with various other things. Sometimes European languages, sometimes math symbols, sometimes whatever. Eventually, standards arose, and there's one called, the usual one is called Latin 1, and it's also called ISO 8859-1. And this takes, again, the first, the low order characters, 0 through 127, all the things with 0 as their high order bit, just correspond to ASCII, so it's nicely backward compatible. And the upper order bits are, and the upper things for Latin 1 are devoted to characters for Western European languages. So various sorts of accent marks and letters that cover most of the languages of Western Europe, as well as, I think, the currency symbols for them. So this is very commonly used, and this is essentially the native file system format for lots of operating systems. When you write a text file on an operating system, you need to know what, when you're using an editor, what does Emacs write the thing out as, okay? And if you're writing English, it'll write it out as ASCII in the ASCII subset of Latin 1. But you can also write out, using fancy editors, Latin 1 text files. And so this is kind of the native format for American, certainly, Linux and Windows and the like. So 8-bit characters, I should mention that. And this 8859-1 has a whole mess of variants. It actually goes, there's 2 ... up to about 16. And what all these variants are is basically ASCII plus stuff for other languages. So there's like one set that corresponds to ASCII plus characters for like South Slavic languages, North Slavic languages, languages written in Cyrillic, ASCII plus Hebrew, ASCII plus Arabic, ASCII plus modern Greek. Okay, and so you can look up in the standards what that set of character encodings are. The nice thing about them is that the bottom 128 characters, the bottom 7 bits, if the upper bit is 0, is always good old-fashioned ASCII. So this gets us through most of the way through Europe and even through a lot of the Middle East. But when we hit the Far East, we run into problems with character-based languages to write, and so we just don't have enough room in our 128 bits to encode these. So you need bigger spaces, and there's 2 of these, or there's actually lots of these, but there is a character set called Unicode, which is a mapping, a larger mapping of characters. And to be clear, I guess Unicode is actually a character set, and UCS2 is an encoding. UCS2 is an encoding standard that uses 2 bytes to encode characters. So you get 2 to the 16th characters instead of 2 to the 8th characters. Unicode provides a mapping for those 2 to the 16th numbers to the actual characters. Unicode gets you, well, the bottom 128 characters of Unicode are again ASCII, which is nice, except that reading a Latin 1 file and thinking it's ASCII works just fine because they're both 8 bits. Reading a UCS2 file and thinking it's ASCII does not work, even though the bottom 128 characters are the same. They're going to be represented as 2-byte units. The upper byte will always be 0, but nonetheless you have to know you're reading 2-byte characters. So if you have a Unicode file and are reading it into a program that understands ASCII, you have to strip off the upper byte. And similarly, if you're writing ASCII to Unicode, you have to add a byte that's all zeros. This gets you most of the Chinese and Japanese characters, not all of them. And it's the native format of Java, and it can be the native format of Windows if you switch the right flag. The disadvantage, if you are working only in ASCII, of course, is all of your strings blow up by a factor of 2. And so you're wasting a little space, but in the old days, that was probably an issue. At the moment, it's probably not an issue. Probably the bigger problem with this is the hassle of translating from the native file formats to the internal file formats. One other encoding that you should know, since it's common in XML, is tries to get around both the problem that some character sets don't quite fit in Unicode, and also the fact that you have to use 16 bits for every character. There's something called UTF-8. There's also a UTF-16. There's also a UCF-4, which uses 4 bytes per character, which gets you many more characters. This is unlike this and ASCII, all of these have a constant number of bytes per character. Here it's 1, here it's 1, here it's 2. So it's easy to index into a string. To get character 5, you just multiply 5 by the number of bytes per character, and you end up in it. UTF-8 is a variable length scheme. Okay. Some characters take 1 byte, some characters take more than 1 byte. And the nice thing about it, or a nice thing about it, is that all of the 1-byte characters with 0 in the upper bit are, again, our friend ASCII. So basically, UTF-8 is entirely backward compatible to ASCII. If you have a ASCII file, you can think of it as a UTF-8 file, and it just works. And then the high order bit is used to indicate that this is the beginning of some multi-byte character. And so you can use various encoding schemes where maybe this sequence of bytes tells you how many more bytes to expect, and then you can just add on a number of bytes. And using a coding scheme like that, similar to a Huffman coding scheme, you can efficiently encode an enormous amount of characters. And you only use the cost of encoding the long characters. You make long encodings for the infrequent characters, short encodings for the frequent characters, and your statistics mean that your average size is pretty small. So the good news is that if you're working in Java, you don't have to worry about all of this. Java, the reader and writer classes that we had in Java, the reason we have them and the reason we have some of that nuisance in the I/O library is that it automatically translates to the Java native format, which is Unicode. All right. Now, how does it know what format it's translating to? Well, in a little bit, it has to guess. It basically has to guess the native file format. If it doesn't have any other information, it uses the native file format of the machine. So a Linux machine running in the US is probably going to be Latin 1 unless you've set it to something else. and or you could set it to run Asian character sets and set the native file format to Unicode. Okay, there's lots of other formats, by the way, that have kind of grown up historically. There's a scat of them, and Java deals with some of them and probably punts on others. Here's a question. Say you're downloading some file from the internet. Okay, how do you know what format it's in? And here it gets harder because you can't guess based on the local file system because you don't know where it came from. And here there are two ways, one of which it can be tagged. In HTML, there's a content header thing, which would be encoding, or something like that, and character set. And so the header would come down in ASCII, and then you could read the encoding content flag, and that would tell you what to expect the rest of the text in, what encoding to use to do this translation. Or in XML, there is a way to kind of self-tag the files. So the first couple characters of an XML file are predictable. They're always going to be in whatever encoding the file is. It's always text. And then there's another flag somewhere also that's encoding. And so by some combination of picking encodings until you get this to look right and reading the encoding tag, you can eventually figure out what encoding the thing is in and what to do with it. So, as I say, in Java, you don't have to worry about this because the reader and writer classes do it for you. Well, you don't have to worry about it for files because the reader and writer classes do it for you. If you're using another language, you might have to deal with it by hand. And it's not fun. So the last thing I want to talk about is how one, in Java, organizes all of this information. And it's similar to what you would have to build by hand in any other language. So Java comes to our rescue, as always, with a pile of objects. So it has an object or a class called locale, which it uses to basically select all of the string and format stuff that we're going to do. And we make one of these with a constructor, and the constructor, let's see, takes the language code and the country code and gives you an object called a locale that you don't really do much with except pass to factory methods to say, give me a something that fits this locale. And Java gives you a bunch of factory methods for lots of things that you want. For example, the number format class has a bunch of methods on it to parse dates and to format dates and to parse currencies and format currencies and whatever. And you get these. You can get a localized version of a number formatter from a factory method on this. So one thing I should mention is there's one called, you can get something called get default locale. There's a factory method which tries to figure out from knowledge on the system where the program is operating. So it just reads some system parameter and does it. So number format equals, and here we're not calling a constructor, we call one of our factory methods, which we talked about. Format dot, I think there's one called get currency something.
A factory method, what does that mean again?
This number format?
Yeah, well, why is it called a factory method?
Oh, factory method is like a constructor, except it's basically a method on a class that's sole job is to build other objects and give them to you. So it's sort of like a constructor, except it's not a constructor, it's a method. But it's just going to return another type of instance for you. It's something that you you do to generate instances. Like in this case, this number format class knows how to build number format objects based on various locales. And that's technology is much harder to build in a constructor, but it's easier to build in a factory method. Okay, it's one of those design patterns we talked about the other day. And you'll see lots of things that have factory methods. But it's get currency something. What does it say in the notes? Instance? So once you have this format object, you can then, once you have this currency instance, basically gives you a currency formatter. You can also ask for a number formatter. There's all sorts of formatters that this factory method will produce for you. And you have to pass in a locale, and it'll give you the localized version of one of these. And then you can say format.parse of a string to convert it to a number, or .format of, say, an int to convert it to something that will print nicely in the language that you want.
Is this relying on the local operating system, or does Java have to know it has to know about that language to be able to?
Right. It gets the locale probably from, when you pass it in the locale, either by making it or getting the default locale. And somebody at Sun has built a bunch of these things for lots of languages. They probably haven't covered them all, so that may return null. Or it might just punt and return the English one if there's some locale that they haven't done it for. So, if not, you would have to make your own formatter. Or just do something different. There's a similar scheme for dates. I think it's a date format object rather than a number format object. But I could be wrong. Anyway, similar scheme. And there's a similar scheme for collators. So you can get things that will alphabetize for you based on locale. The final thing to worry about.
Is there anything like translation?
No. There you have to go hire somebody or lots of people. So you have to take all your strings in your UI that you want to do, and you have to hire somebody to translate them in each language. So let's talk about strings. We have all of our pile of strings that we want to use in our UI. The first thing we have to do is translate them into each language. Okay, so now we have n piles of strings, one for each language. And we need to organize these things so that, A, our program has to figure out how to use them, and then we always are using the right set for the locale. And the scheme for doing this is not quite as elegant and quite a bit more primitive than the scheme for doing formats. But the basic idea is for all of your strings, you kind of put them in a class, and you build an accessor method for them. And you can build that accessor based on to have hash table semantics. So you give the accessor method a keyword, and it gives you back the string corresponding to that keyword. Or you give it an index and say, I want string number 3, and it gives you back string number 3. And string number 3 should have the same meaning in all of these sets. So now when you're building your program, you never build in the string itself. Okay, you build in the key to that string and a call to this accessor method to get the string. So you never actually build in string constants anywhere. You build in, something like get string of some keyword, string 1, or something that's probably more mnemonic to the type of message you want to send. Any place you would have a string constant, you would build one of these calls instead, and this would be called on this object, which I'll call bun. So you would call bun.whatever. I call it bun because these objects should inherit from something called resource bundle. And resource bundle does not help you write the accessor method at all. That's up to you. You can also use this scheme for not only do you want to localize anything you want to localize, like not only strings, but say you have a bunch of images. Some images are appropriate for one culture, some images are appropriate for another culture, and you want to index the, instead of using the same images all the time, you want to, again, index them and then pull in the locale-specific index. So once we have, once we've loaded the right class into bun, which is of type resource bundle, we can then call the successor and use the scheme everywhere. So now the only problem is how do we get the right one loaded? And what we have is a bit of a hack. All right. The hack is that you take all of these guys and you build them into classes with a current naming scheme. So you make up some name. I'll just use my bundle. And then underscore language, underscore country, dot class. All right. And so you build one of these guys for every language country combination that you have, dot, 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 dot. And maybe you make a generic one. And maybe you make one that's just a generic English one that assumes that, English is English. And then you can call another, not quite factory method, but a method that will get the right one. So we can say bun equals, there's a static method on resource bundle, which is most of its reason for existing, dot, I think it's get bundle. And then you give it the keyword that you've called your class as a string. And then you give it one of those locale objects that tells you what locale you're looking for. And it will grovel around your file system and try and get the best match to the language country combination specified in the locale. And if it finds an exact match, it will return and load that. If it doesn't find one of those, it'll drop back and try and find a language match. Otherwise, it'll return the generic one. So basically, you've built a whole mess of classes. Each one really does nothing but store a whole mess of strings and maybe other stuff. This mechanism lets you select one and load it into your program, and then you use this scheme to only use, so you never actually refer to any strings. You always use the strings in the bundle, and everything works. It's not particularly enjoyable, but it does work.
I would have thought they would have had separate versions of the program for different
Well, but that's, if you just copy the code all over the place, then you have the problem of bug fixing in, 27 different copies. And so this lets you only duplicate the things that are different and share everything else.
What about languages where the natural display of characters doesn't go from left to right?
That's true. What you would like to be able to do, I suppose, is put in your resource bundle object maybe a factory method that gets the right text fields elements, okay, for each particular display, right? So since this is something that you write, you get to put whatever methods you want in there and have them do arbitrary work. So, as I say, it's really kind of a hack framework that pushes most of the work on you. Now, in the worst case, you actually have to write the display mechanism that will do non-left to right, top to bottom character display.
Can you set a flag and switch Microsoft Office to German?
To German in what sense? You mean get all the displays in German? You probably could, since
Is it all written into the code?
It's not in the default one. If you buy different versions.
Right.
Buy
If you buy an American English only version, but there might be a generic European version you buy that has most of them in, and so.
Actually, the generic one you buy in this country comes with French and Spanish.
Does it? So you can switch to French, and so yeah, you may, in principle you can, but they tend to charge you for extra stuff. And though my old office mate had basically the entire Japanese system. She would write email in Japanese and type Emacs in Japanese, and had all that working on her system. I think it was something she separately had to install that didn't come natively, but this was on Windows, and it all worked fine. That's all I have to say about internationalization. And since this is the last lecture, I think I should present a summary and leave you with some take-home lessons of what I think the important bits of information out of this course are, since you can only really remember a couple things from any course. So, let's see. We've gone through a lot of object-oriented programming technology and we've seen a lot of common programming paradigms. So I think principles and a lot of programming paradigms. And I hope we have seen these in situations, or at least they've been presented, even though we've used them in Java, in a way that you could translate them, or at least see how to translate them, into other domains. Since all of the ideas we've talked about port directly and are used universally among systems, although the syntax is different. The other thing we've talked quite a bit about is kind of design methodology. So, let's see, our OOP principles. It's good to always start from the beginning and think of what we are trying to accomplish. It's always good to have our ultimate goals in mind. So we want our program to be maintainable, extensible by other people. Let's see. Clarity, we want it to be well documented and easy to understand how it works. And we want efficiency. Okay, and here we really want both programmer and program efficiency. We want it to run fast, and we want it to be written fast. And finally, we want reliability. We want as few bugs as possible. Okay, so here are our goals. And we have some principles of programming which help us with this. I'll mention two, which you could probably put everything else into, depending on how you define them. Encapsulation and abstraction. Okay. Encapsulation covers things like separating the implementation from the interface, separating having a clear division between the code that uses a class or some data and the code that implements it, and hooking these things up, So things that help us with this are access control. If we think of the language features, classes themselves, the idea of interfaces, which abstract completely the set of methods that you call from the implementation, things like that. Abstraction helps us with code reuse. Okay, one of our principles is we want to write every algorithm once and reuse it as much as possible. And we want to which means we either want to put it on a parent class and use it for a bunch of child classes. So for that, inheritance comes in handy. We can put all the common stuff on a parent class and only the different stuff on child classes. And finally, we would like to, from another point of view, write our algorithms in terms of abstract instantiations of classes or ideas of classes, and then have them work for all of the low-level child classes. And the mechanism that makes that work for us is polymorphism. Okay, so here are kind of our OOP tools that we're using to try and implement these ideas. So that really, I think, is the essence of object-oriented programming, basically using these tools to achieve these principles, to achieve these goals. So this set of 5 things probably close to defining object-oriented programming. So what else did we talk about? We talked about programming paradigms, various ways to organize your program and write programs. We started out with just normal sequential memory-based programs where you just do some arbitrary computation. We then talked about event-based programs. Okay, a more sophisticated type of control, or at least a different type of control, where instead of writing something that goes from A to B to C, you write a bunch of handlers for events that happen, which are either buttons clicking. We saw this mostly in GUI applications, but you could easily do it. Think of it in terms of network-based applications too. Every time you get a network packet of a certain type, you treat it as an event and dispatch on its handler. And we talked about multi-threaded code and synchronization, which is, again, a more complicated but also useful way of organizing programs. When you have to block on many different things in parallel and want to have many different things going on at the same time, either in a sort of parallel architecture or a pipeline architecture. We talked about other programming tools, exception handling with catch and throw, which is pretty universal. What else we talked about? We talked about Stream.io. We talked about GUI and Windows system ideas, which is also pretty universal these days. And we talked a little bit about networking, which is really, I think, you can think of almost as an add-on to Stream.io. There's not really anything too new to use in networking. It's just that you have to know that the network's out there and there's a whole new set of errors to deal with. Stream.io. So that's basically the set of paradigms we talked about. We then talked about a bunch of advanced ideas, mostly for cultural purposes, how these ideas port to web programming, how they, we talked a little bit about components, databases, the next level of thing that there's really no new programming paradigms in or OOP technology in. It's just a new application area that you apply your tools, and there's a bunch of libraries to learn and the like. Finally, let's talk a little bit about design process and leave you with some, let's see, final aphorisms. Let's say, think first, code last. Always a good idea. Whenever you have a new programming problem, put on some music, put your feet up, and stare out the window for at least the first day. And write stuff out on paper, and maybe sketch out classes in documentation form, but don't even think about writing any code. Let's see. You want to do your design and specification in general top down. think of the big pieces, how they divide up, how they interface with each other, and maybe do another level and think about how the pieces that do that. In general, you probably want to, once you've spec'd it all out, implement and test bottom up. Incrementally and do unit testing. So take your basic things that you've built, test those, then test the integration of those with something else. Called unit testing. Lots of people like it. Finally, what? I should have another aphorism here. Oh, yes. An easy trap to fall into. I used to be guilty of this a lot myself, but I'm better. Which is to build functionality and clarity first. Build your design so that it's clear how it works and so that it gets the job done. And then, only then, once it's all working, profile it to see where it's slow and optimize. It's really easy to kind of get paralyzed when early on in the game implementing some data structure or something that, just to get paralyzed thinking of how you can implement this efficiently so it doesn't slow down the rest of your program. Don't fall into this trap. Just go do the absolutely simplest implementation you can possibly come up with that will get the job done. Use a standard library tools if you can. Then, once the whole thing is running, so it makes your design as clear as possible and as simple as possible, but nonetheless does the job, then when you get back, then profile your program. There are tools for running data through it and seeing which methods are slow, which methods get called a lot, and are taking all your time. Then go back and optimize those. Okay. Otherwise, you can spend a lot of energy optimizing something that never gets called, and so you've wasted a lot of time on nothing. And it's hard to know ahead of time where the critical paths are. So try and this is a natural impulse, and try and avoid it. It's taken me a while to get over it. And that's about it. That's the end of the course. There will be no lecture tomorrow. And you guys will talk, and we're going to film you this afternoon. And thank you all. It's been really fun teaching you all, and you've been a great class, and you've accomplished a lot, and I'm really, impressed with what you've done with all the problem sets. And thank you very much.